Alright, so we've seen several of these limit properties and kind of how they work with some of the limits with algebra, polynomial, rational, composition, and we've seen a little bit of intro into the sandwich theorem. And I want to look back on the problem that we just completed with the sandwich theorem, which is looking at the limit as x approaches 0 of sine of x over x. And what we showed in the last video was that that limit was equal to 1 by examining the sandwich theorem and evaluating the limit of the cosine function as well as the limit of the y equal to 1, and we showed that both of those limits approach 1 as x equals to 0, so therefore the limit of sine of x over x also approaches 1. Alright, so we're going to start using that fact, and we're going to use the fact that once we know this special limit, that we are going to be able to do other limits that are of the same form. I also am going to leave for you, if we have not done that yet in a video, you might want to use your calculator to investigate the limit as x approaches some value c of 1 minus cosine of x over x. Let's do 0 here. And if you investigate this limit on your calculator, you will see that that limit is equal to 0. So basically, just justify to yourself as needed that the limit as x approaches 0 of sine of x over x, which of course is that 0 over 0 indeterminate form, which means do more work, that limit is always equal to 1, which we proved by the sandwich theorem, and you can verify on your calculator, and that the limit as x goes to 0 of 1 minus cosine of x over x is going to be 0. Now how we're going to use these facts is basically just memorize them. And from now on, anytime we're taking the limit, and if we're taking the limit as x goes to any value, and that value happens to make the denominator 0, we basically would get 0 over 0 in that indeterminate form. If it is in this form, even if you have not an x in this location, but you have any function here and any function here, as long as these two things match, we are going to be in this form, and we can always conclude that that limit is going to be equal to 1. The same thing is true when we see the limit that is the 1 minus cosine of x over x. It doesn't really matter what functions are in these two locations, that if the limit as x approaches c of the bottom is 0 and the limit of the top is 0, so we have that 0 over 0, if it is in this form, then what we know is that that limit overall is going to approach 0. So we're going to kind of shortcut our do more work because we're just going to memorize these two special limits. Okay? So for example, if I look down here, I try to substitute in 0, I end up with sine of 0 over 0, which is 0 over 0. So I'm getting the indeterminate form, which is do more work. But I recognize that when I take a look at this, I essentially have the same function here and here, so I am in the correct form. So I get to conclude that the final answer of this is nothing more than 1. Done with the problem. So that's our do more work. Do more work is recognize the special form and answer the question. Same thing is true over here. If you take a look at part B, again, these two match. If we were to plug in, try our direct substitution, which is always our first go-to to see if we actually need to do more work, we would have 1 minus cosine of 0 over 0, which would be 1 minus 1 over 0, or 0 over 0, which means do more work. But we recognize our do more work in this case is, oh, this is that special form for that trig limit when you have the indeterminate form, so I can pretty much just say my answer is going to be 0. So you just have to memorize 1 and 0. And this limit works even if it doesn't really matter where x is going. It's the fact that the limit on the bottom is 0. When I plug x equal to 7 in here into this function, I'm going to get sine of 0 over 0, 0 over 0. That's what we're looking for with this special limit form. So, and like I said, and as long as you do have to make sure that this function and that function match, as long as they match, we can make the conclusion that that's equal to 1. Now, let's do a little practice with some problems where you might have to use these memorized limits in conjunction with your limit properties. You might have to do a little algebra. So like initially when we take a look at this, we try substituting. We get 0 plus 0 over 0. So that's the 0 over 0, do more work. This is close to, if you just look at this part right here, that's close to that special form, but I've got this extra x. So what you're going to recognize is that you can basically do a little algebra. That's going to be our do more work. I can split this fraction into two fractions, basically uncommon denominator it. And when I uncommon denominator it, my own made up word, I'm basically going to be taking the limit as x goes to 0, the sum of 1 and the special limit sine of x over x. And provided both of these limits exist, the limit of a sum is the sum of the limits. So we can come down here, take the limit of 1, take the limit as x goes to 0 of sine of x over x, and end up with limit of the constant is 1 plus the special limit of 1 to get my final answer of 2. So sometimes you just have to do a little algebra, recognize that you have that special limit in there, and try to manipulate it algebraically to pull it out so you can apply your limit properties. Here's another example where, again, if I try to plug in 0, I get 0 over tangent of 0, which is 0 over 0. So we're going to do more work. We don't see initially that you have a special limit sine of x over x, but what we see is we've got a tangent, and sometimes we need to employ a trig substitution. So we're going to do the limit as x goes to 0 of x over sine x over cosine x. That's going to simply give me, now I'm going to rearrange this a little bit. Using my fraction rules, and hopefully you'll remember them, I can keep these together, or you can think of dividing by sine over cosine is the same as multiplying by cosine over sine. So that's going to give me x over sine x times cosine of x. And I did split it this way in particular because I'm trying to pull out the special limit that I'm looking for. I see I have x over sine x. And then I have this limit, and I apply it to the cosine x. And I think, okay, I think the limit for as x goes to 0 of cosine of x is going to exist. This limit exists, and the limit of a product is the product of the limits provided they exist. So I can split this to the limit as x goes to 0 of x over sine of x times the limit as x goes to 0 of cosine of x, which is simply going to give me my final answer of 1 times plug in 0, cosine of 0 is 1, so the final answer for that one is 1. So you used a trig substitution and did a little algebra to manipulate it to pull out this special limit so that you could then use your limit properties. The limit of a product is the product of the limits provided they exist. Alright, let's take a look at part C. Alright, so taking a look at part C, again, trig, we don't have the cosines, but we have secant, which is related to cosine. So we have to recognize that maybe a trig identity substitution is going to be in order here. So I'm going to basically think of this as cosines. So I'm going to do the limit as theta goes to 0. And again, I know I have to do more work because when I plug in 0, your secant of 0 is 1. So 1 minus 1 is going to give me a 0 on the top. And here, let me change color just so we can tell the difference between these. And when I plug it into the bottom, 0 times 1 is going to give me 0. So I do have the 0 over 0 do more work. So when I calculate this limit, I recognize that it's sort of like the special limit with the cosines, but I have secants, so I'm going to change them to cosines. Secant is 1 over cosine theta minus 1 over, this becomes theta over cosine theta. And dividing by cosine theta here would be the same as multiplying cosine of theta to the top. So we'd have theta going to 0. I'm going to leave the theta on the bottom, and I'm simply going to pull the cosine, flip and multiply to the top. And when you multiply that cosine times 1 over cosine minus 1, we're going to end up with the limit as theta goes to 0 of 1 minus cosine theta over theta, our special limit, which is 0. So we're recognizing that we have something close to a special limit that we know, and this is directly related to it through a trig identity, so we use a trig identity. And then I can basically manipulate my way algebraically to get the special limit and make a conclusion. Now over here we have a little trick that we're going to employ. And before I do this problem, I'm actually going to come back up here to the top and I'm going to do a kind of a side example. And the side example I'm going to do, let's just call it part D up here, is going to be, what if I wanted to do the limit as x goes to 0 of sine of 5x over x. So if I see this problem, the issue that we have is that this function and this function, they don't match. I try plugging in and I'm going to get 0 over 0, which is do more work, but what I see is I can't quite go straight to the special limit because I have to have these two functions matching. But what we're going to do is we're going to employ convenient use of multiplying by 1. Because anytime I multiply a fraction or anything by 1, it doesn't change it. But when I multiply by 1, I'm going to multiply by basically a really special form of 1. So what I'm going to do is I'm going to multiply by a fraction. So I'll take out this 1 that's here. And the fraction that I want to multiply by, I'm going to choose, what I'm missing here is a 5. So I'm basically going to multiply this expression by 5 over 5, which is 1. It's not changing the expression, I am just putting it in a nicer form by using this trick of multiply by a form of 1. Now I can apply just basic algebra properties. This is the same as saying the 5 times this 5 right here, I'm just going to pull it to the front, and then I'm going to take the sine of 5x, and then this 5 I'm going to put with that x on the bottom, 5x. So now I have the limit of basically the product of two limits that both exist because one of them is a constant and the other one is the special limit over 5x. And so your final answer would be 5 times 1 or 5. So anytime we're missing a constant, we can add it in and with a use of this form of 1. And sometimes you can add x's in as long as you're missing x's from both the top and the bottom. Alright, so now let's come over here and let's take a look at this example D. So in example D, I'm going to check, I'm going to let x go to 0. You would get sine of 0 over 0, and then there's a cosine of 1, which is, or cosine of 0, which is 1 there. But you're going to get 0 over 0. I'm going to conveniently rearrange this. I can sort of see I'm almost where I want to go. If I take the 4 over the cosine of 2x, I'm going to group those together. And then I'm going to take the sine of 5x and I'm going to group that with the x. And what I see here is very similar to the example I just showed you above. This limit exists because if I plug in 0 in for the x right here, I get cosine of 0, which is 1, and that's 4. So this has a limit that exists. So I'm on target to use my limit properties. Over here, if I could just get a 5 right here, then basically I would have the special limit. So I need to put a 5 in here. And then what I have to remember is I can't just stick a 5 in there. Whatever I put in there, I'm really only allowed to multiply by a form of 1. Now I could do the same thing I did above and do 5 over 5 and then rewrite it a million times. But what we're going to recognize is that basically all I got to do is put a 5 here and then make sure you put a 5 in the top of the fraction and just put it in the other one that you're going to calculate your limits with. And then so we want to calculate it. The limit of a product is the product of the limits provided they exist. And the reason we split them the way that we did was so that we got two limits that exist. And so I plug in my 0 here and I get 20 over cosine of 0, which is 1, times this one, special limit 1, so my final answer is 20. So we employ this trick of adding in a form of 1. Alright, let's take a look at part E. Again, same kind of idea. We kind of look for whenever you see these ratios that it's got to be one of those special ones. I see a tangent, which doesn't help me. I check plugging in. As x goes to 0, I am going to get 0 over 0, so I know I have to do more work. So I'm going to start by rewriting the tangent so that I can get it into sines and cosines. So that's going to be sine of 3x over cosine of 3x, and that's all divided by sine of 4x. Okay. I'm going to employ some use of basically algebra, okay? Kind of see what algebra skills you have. I was trying to ungroup that and change the color, but just kind of work with me that that's a different function, so I don't have to rewrite it. I'm going to rewrite this. This is like over 1, right? And so dividing by a fraction is the same as multiplying by the reciprocal. And I'm going to group things together. I'm going to take that sine of 3x and put that in a fraction by itself. I'm going to take the cosine of 3x and put that in a fraction by itself. And if you want to, you can put a 1 there. And then this one, when I flip and multiply, is going to be 1 over sine of 4x. And at this point you may be going, I don't have the special property because I don't even have an x in this location, much less a 3x. But what we're going to look at is you say, well, alright, if I had a 3x here, that would be great. And if I had maybe a 4x there, I might be able to do something with that because that would match this up and it would be sort of close to the one that I'm looking for. And if I could do that, then it would work out fine. So I'm going to start looking for a form of 1 that I can add in. So I can definitely put in, let's put in a 3 and an x here. Okay. Now I can put an x here, which I needed, and notice x over x, that's going to be 1. This 3, I haven't balanced yet. I'll stick a 3 there to balance this one out. So I'm still in a form of 1. And then I come over here and I go, I think this one needs a 4. But when I put a 4 here in the top, I need to put a 4 in the bottom. And again, I'm going to put it here because this is the limit that exists and is the target for the limit of a product is the product of the limits. So, and if you check all of these, I've basically done nothing. I've got a 12x in the top and I have a 12x in the bottom that I added in. I added in a form of 1. I just added in conveniently where it helps me. That's the magic of the form of 1. So this limit we can do. That limit is going to be 1. So we're going to do the limit as x goes to 0 of sine of 3x over 3x, which is going to give me 1, times the limit as x goes to 0 of the 3 over 4 cosine of 3x. We plug in 0. Cosine of 0 is 1, so I'm going to end up with 3/4 as my limit. So we'll go times 3/4. And then over here, I go, well, that's really, really close to the limit. It's just flipped. It's the reciprocal of it. So I'll show this step this time, but we usually never write this step, but I'll show it to you. I can rewrite that fraction as 1 over sine of 4x over 4x, the reciprocal of what's there. And now I have the limit of a division where both the limit on the top exists and the limit on the bottom exists. So the limit of the top is going to be 1 and the limit of the bottom is going to be 1, and notice that this ends up being 1 as well. So pretty much from this point on, of course my final answer here is 3/4. If we see the reciprocal limit for the sine one, now only for the sine one, so maybe we'll put it down here in a box, that the limit as x goes to 0, if I get x over sine x, that is also equal to 1, because the reciprocal of 1 is 1. Okay? Do not use this rule with the cosines, because the cosine special limit is 0 and the reciprocal of 0 does not exist. So that's not going to work when we do it with the other trig special one. Alright, and then let's take a look at this one and we'll play around with that. Alright, now keeping this in mind, you are going to be tempted with this one to maybe try to work with the fact that it's close to 1 minus cosine of x. Like for example, maybe, and write this in pencil because we're going to erase this, I'll warn you ahead of time, that if I multiply this by -1 over -1, which is a form of 1, I'm going to do the limit as x goes to 0. It's going to give me -3x squared over and then 1 minus cosine of x. And then you go, well, maybe I could split this and I could end up getting negative 3x. I'll write it and then I'm going to erase it here in just a second. X goes negative 3x times x over 1 minus cosine of x. Now you are going to be tempted to take the limit here and then go and take the limit here, but you got to be careful because the special limit for the cosine that was the reciprocal of this is 0, and the reciprocal of 0 does not exist. So this is not going to work because remember our limit properties, the limit of a product is the product of the limits only provided they both exist. So this is not going to help me for this problem. I just wanted to show it to you because it's definitely something that you might, sometimes you head down the wrong path and that might be a path you head down. So we're going to come back here and we're going to restart this problem and we're going to talk about a form of 1 that we might want to use. Now in this problem what we're going to see is that I see cosine x minus 1 and I go, well, it's kind of not great for me because it doesn't really match. I'm going to use, and we did this in Trig last year when you were talking with Trig identities, sometimes we use what's called the conjugate. And I'm going to multiply by that form of 1. And I'm going to see what happens. Now, and the reason, and I'll tell you why my target is going to be that, is when I multiply this, and I'm just going to keep the top 3x squared times this cosine x plus 1 over, now when the bottom, when I multiply this out, I'm going to get cosine squared x minus 1 because you FOIL and the inner and the outer terms would cancel out. And when you see that, what you kind of need to start thinking about is, wait a minute, isn't that one of those Pythagorean identities? And it is. Cosine squared x minus 1, it's not quite what I need. If I had 1 minus cosine squared x, I would put sine squared. It's the opposite of what I need. So it's going to equal negative sine squared x. So I'm using a Pythagorean identity, and I am basically going to take out, leave this cosine x plus 1, this cosine squared x minus 1, and turn it into minus sine squared x. And now when I do that, what I am going to be able to do is I'm going to be able to work with this now and kind of see how I can split it, because now I've got x and sine x's, because isn't sine squared sine x times sine x. I'm going to be able to split this. And I obviously did not leave myself enough room, so I'm going to employ the use of an arrow just to come right down here. So now we're going to do the limit as x goes to 0. I'm going to pull out things that are grouped together. I'm going to do an x over sine x. I'm going to do an x over sine x. So that's x squared, and that's the sine squared. And then I'm going to take the negative, just put it with a 3. And I'm running out of room here, but can I just do parentheses and say that's all that cosine stuff that's left is going to go there. So I have the limit of the product of 3 things. The first one, limit of the first factor is going to exist. Limit of the second is going to exist. Limit of the third is going to exist because you're not going to have division by 0 because you didn't even have a fraction left over here. So your final answer for this one is going to be the limit as x goes to 0 of x over sine x times the limit as x goes to 0 of x over sine x times the limit as x goes to 0 of negative 3 times cosine x plus 1. And then I'm just going to change color so I can save some space. This limit is going to be 1. That limit is going to be 1. This one we plug in 0. Cosine of 0 is 1. 1 plus 1 is 2. 2 times negative 3 is negative 6. And so when I multiply these all out, my final answer is negative 6. So you manipulate and separate so that you get the product of 3 factors that you have limits for. And that's the key. The limit of a product is the product of the limits provided they exist. Alright? And going back, doing a little bit more sandwich theorem here, I have a function g that I am interested in the limit, and it is sandwiched in between the top piece of bread, or actually the bottom piece of bread and the top piece of bread. So immediately I know my target is probably sandwich theorem. So I come in here, and sandwich theorem says take the limit as x goes to -1 of the bottom piece of bread. So we calculate that. So kind of step 1. And this is going to give me direct substitution 3. I calculate the top piece of bread's limit as x goes to -1 of x squared plus x plus 3. If I plug in -1, I get 1 minus 1, 0, plus 3, which is 3. Oh, yay! We're excited because I now see that I can use the sandwich theorem because I did have the bread smushed together so that it gave me the limit I was looking for. So number 2, we just make a conclusion by the sandwich theorem. I also can't spell. I know there's no H in that. The limit as x approaches -1 of g of x would have to also be 3, and we're done with that problem. So it's, quite an easy concept for the sandwich theorem. Just thought I would throw one more example in. All right, and that concludes our examples of using the special trig limits in conjunction with the limit properties that you saw in the previous sections.